Today's lecture is on forced harmonic oscillators and resonance, and whereas the last two lectures I like to call things on springs, today's lecture is things on swings. So I encourage you all somewhere after today's lecture to go down to your local park and do something that you perhaps haven't done since you're about 5 or 6 years old. Which is to jump on a swing and have a bit of a play, because probably the best physical example I can think of forced harmonic oscillators and resonance is riding on a swing. And the idea here is that you essentially have a pendulum system. It's got a little bit of damping, so if you just sit there and not do very much, you'll gradually wind your way down, and it's a weakly damped system, so it takes a little bit of time to do this. And this is some mix, as we discussed yesterday, of friction in the system, wind resistance as you move through the air, and maybe a little bit of the flexibility in the ropes or chains that you have hanging onto your swing. And then the thing that you learn very quickly as a kid is that when you hop on one of these things, someone gives you a push, and then eventually the person who's giving you a push gets rather bored and doesn't want to do it anymore, and you have to find your own way to generate swinging motion. And we all learn very, very quickly that there's a technique into this, which, you know, some people are very effective at kicking out legs and so forth. Most of you will know it. If you haven't, go down the park, give it a try, work it out for yourself. You'll actually find that what you're doing is making a motion with your body that is at the same frequency as the swing and at a certain phase relative to the swing, okay? And if you do that, you end up driving that oscillator, and you can go from doing very small swinging motions to quite good swinging motions. And if you're a crazy adventurous 10 or 12-year-old, you suddenly learn that you can actually almost get to round near the top, and you start to stop then because you realize that the mechanical structure of the swing may not hold on, and things may get rather exciting and result in broken bones, okay? So what we have here is actually a really good example of resonance, and different to the example that I gave yesterday of the Tacoma-Narrows Bridge, because here you actually have a driving force that really is coupled in frequency and phase to the system and driving that system very directly, okay? Okay, and as you know, if you drive that system very hard, you can drive it to the point of essentially letting go. And so one of the classic examples for resonance is the shattered wine glass. And you can see here basically a wine glass in front of a speaker with a frequency being played at it, which is very close to the resonance frequency. You can tune that in. They're watching in this video with a slow motion camera. And if you drive the amplitude of the driving oscillation up far enough, you can drive the system to the point where it just basically fails mechanically. And so here you can see the slow motion footage of the same thing. It's oscillating very strongly at its natural frequency, and eventually it can no longer take it and it gives away. Today's lecture, I basically want to build up a mathematical framework for handling these types of systems. And so in the first half, what I'm going to do is start from just a simple mechanical oscillator with a damping term and a forcing term, and get to the point where we have an amplitude and a phase equation, and we know where the maximum amplitude is. And then in the second half of the lecture, I'm going to look in a little bit more detail at the actual structure of the amplitude as a function of frequency, and delve into some important parameters related to that maximum that we have in a resonance system. Okay, so what we have is our familiar mass on a spring setup. I've kind of made it simple here by removing the spring and removing the frictionless surface and so forth. And what we have is basically a mass oscillating about some equilibrium position in the middle, which we've called x equals 0. And we need to write ourselves a force equation here. And the important thing is, at least from a Newtonian perspective, when you write force equations, you need to know the magnitude of the force. You also need to know what direction it's operating in, okay? And so you can see here that we have our spring force is always acting to try and restore the system back to its starting position. We have, so this is looking at the motion of the particles. This is when it's moving in, this is when it's moving in, this is when it's moving out, this is when it's moving out. So this is not quite at the ends of the motion, not quite at the middle, it's on the two sides as a diagram. We have a damping force which always acts opposite to the velocity, and so you can see here sometimes it acts with the against the spring force, sometimes it acts with the spring force, depends what part of the motion you're in. And you also have an external driving force that we're adding in today, which is a sort of an F equals F naught, so an amplitude EI omega t, so it's an oscillatory force that adds onto this and drives this system with it as well, okay? And so if we balance this all together, we end up with our total force being equal to our Hooke's force plus our damping force plus our external force. And if we pull this all together, we've basically got mx double dot is minus kx minus cx dot plus f naught ei omega t. And you can pull all the terms together on this thing so that you end up with mx double dot plus kx. Let's put the terms in a sensible order here. Plus cx dot plus kx is equal to f naught ei omega t. Okay, and this is a really common thing to do in physical problems, so you'll see this come up in your higher year courses as well. Often you'll separate the spatial terms onto one side and the time-based terms onto the other side of an equation when you write it, okay? And that's pretty much what we've done here, is just isolate the terms on the two sides. It's the same equation that we solved yesterday, except now there's a time-based term on the right-hand side rather than a zero. And so this is a little bit trickier to solve from a differential equations perspective. But what ends up coming out here is the solution is the sum of two separate parts. I'm not going to go in and do that properly because half of me says it's a differential equations course and I'm not here to teach differential equations. And the other half says, if you have a look in Taylor's book, he actually explains what's going on there, despite the fact that it's kind of redundant to a differential equations book. But I'm more interested in the actual solutions here. So the solution is sum of two parts. And when you solve this in two parts, you have the solution to this bit, which is exactly what we did yesterday. And then you need to include an adjustment to that solution that comes from this bit here, okay? And so what we're going to do in here is now include a new component to the solution that's going to add on to the component that we had yesterday that accounts for this new term that we've added, okay? And so again, same approach to doing ordinary differential equations of guessing a solution and then testing that solution. And so what we're going to do is make the inspired guess here that we have an x of t, and given that we've got an oscillatory force, we're probably going to have an oscillatory term in here, okay? So this thing is going to be, we'll give it an amplitude, prefactor at the front, so we can set a magnitude to this thing. E, I, omega t, and we're going to assume that it's going to, this term's going to respond at the same frequency as the driving force. There's no reason not to. And later on we can see if we need an adjustment on this. And we're going to assume that there's a phase term in here just to allow the damping in the system to force the frequency, to force the response to lag behind the drive in the system, okay? Starting trial solution. Might be right, might be wrong. If it's right, great. If it's wrong, then we go back and we add something to it, okay? All right, so we have here an amplitude A and a phase phi that are yet to be determined, but we'll play with this as we work our way through. And so what we need to do is now verify that this is a solution by substituting it into our equation, okay? So we have m d on dt squared, and I'm going to do this step by step so I get all the terms out properly. A e I omega t minus phi plus c d on dt a e I omega t minus phi plus k a e I omega t minus phi up here equals f naught e I omega t. All right. Where omega at the moment is the frequency of our driving force coming into this system. There's no reason to assume another frequency at this point. So if we take this term out the front, we will get an I m omega d on dt a e I omega t minus phi. This term in the middle here will give me plus I c omega a e minus I omega t minus phi. And then we will have the other term here and the thing on the end. Okay, I'm just going to use dittos there just to carry the term down so I don't run out of page space. And then of course we've got one more derivative to deal with right here up the front. So this is now going to be I squared m omega a e I omega t minus phi plus that term equals the term on the end, all right? And if we now clean up the term out the front here, we're going to... Actually, no, we're perfectly okay here. All right, so the next thing I want to do here is divide... I'm going to divide the whole equation through by e I omega t minus phi. And the nice thing about this is I don't have to keep writing e I omega t minus phi's at the moment, which is going to take forever on this video. So we're going to divide all the terms by this. My I squared out the front is minus 1, so what we've got is minus m omega a. Actually, I've dropped a term. There should be a squared there, and that's going to make that a square there, right? Yeah, I'm going to have another omega come down. Good. Okay, plus I c omega a just here, plus ka. Okay, so this has now taken each of the terms and divided that term on the end out. And then my last term is going to have something in here, so this is going to be f naught e I omega t on e I omega t minus phi. And of course I can use the e I omega t in the top with the e I omega t in the bottom to cancel those two terms out. The minus phi in the bottom will change signs and pop up the top, and so this is f naught e I phi. Okay, and of course you know from Euler's theorem that we can write f naught e I phi as f naught cos phi plus I sine phi, like so. Okay. All right. Now, if we consider this equation here, we've got we've got some imaginary parts, which I just highlighted in green, and we've got some real parts in here as well, which I've just highlighted in red. And so what you tend to do in a lot of cases where you get complex equations like this is to split the real parts off, split the imaginary parts off, and deal with those separately, okay? So what we're going to do is do that, and we're going to equate the real terms on the left to the real terms on the right, and the imaginary terms on the left to the imaginary terms on the right, okay? So our real terms over here are going to be minus m omega squared a plus ka is equal to f naught cos phi. And we can write this term out the front here as a k minus m omega squared and get something that looks like this, okay? And let's call this equation 1 because we're obviously going to use it down below to clean up the maths, okay? And then we've got our imaginary component, and of course it's a bit simpler. We've got our c omega a on the left, and then we've got f naught sine phi on the right, and this we can call equation 2 because we're going to use it as well, okay? All right, so we've got these two little equations, and then what we're going to do is very similar game to what we did in it was either yesterday's lecture or the lecture before, I can't remember which one now. We're basically going to cluster the two parts together to get two new things, okay? So the first one we're going to do here is we're going to take 2 divided by 1. And so if we write this thing, we've got f naught sine phi on f naught cos phi. And that's equal to c omega a on a k minus m omega squared. Like so, okay? And then you can probably see where I'm going. The f naughts are going to cancel out. I'm going to be left with an expression for my phase term. So sure enough here I've got tan phi, and we're just going to make it explicit that this phi might depend on frequency, okay? Don't need to carry that all the way through the rest of the maths necessarily in the notation, but I just want to at some point make it clear that I know what this thing may depend on. And of course we can see that here because there's a c omega a on a k minus m omega squared, okay? Now some of you might have gone, okay, well why didn't you write phi as a function of omega and c and a and k and m in here? And the reason why I didn't put all those other things in is that in principle for the given problem, the mass is fixed, the spring constant's fixed, the damping constant's fixed, and maybe even the amplitude of the response. It's less a variable you control, it's more a variable that reacts, or is a variable that's associated with the response of the system, is out. And I've left with the one thing that I'm likely to be changing in my physical system here, which is the frequency, okay? So in a lot of cases, we might write a functional dependence in an equation in physics, and really we're focusing on a variable to make it clear that that's the one we're interested in and that it matters, okay? So we can call this equation 3 just to keep track of things, okay? Really good problem solving and exam technique is sometimes just a number. Don't number every equation, it'll take you all day. Often it's just a matter of being inspired and knowing which ones you're going to use and which ones you're not going to use, and assign them a number so you can keep track of them, okay? So you'll remember in that earlier lecture we did like a term divided by a term to get a tan of a phase angle, and then in an earlier one what we also did was take a square plus a square to get rid of the phase term and isolate the amplitude, and we're going to do that here as well. So the other thing that we can do here is go 1 squared plus 2 squared. So this will be a squared k minus m omega squared plus c squared omega squared a squared. And I obviously wasn't very smart here because I started writing too far over to the right and I've run out of room. So let me actually scrub this and do this again, just so I can keep things neat on the slides. So we've got a squared k minus m omega squared plus c squared omega squared a squared. And this is actually kind of important just while I'm on this point. One of the really tricky things as a marker of exams and assignments is sometimes it's really ambiguous. People will scribble stuff all over the page and you have absolutely no idea where it's going and you can't follow the logic. And in the end, you have to give up because you can't give marks because you can't work out what they've done. So getting into the habit of at least putting some semblance of sanity into your flow in your maths is a very, very good habit to get into. And it's a good reason to do lots of problems because you get used to it after a while. Okay, so this will be now f naught cos squared phi. There'll be a square just here. Plus f naught squared sine squared phi. Okay. We can collect the f naught from this, and just to be really clear on this, this is now going to be cos squared phi plus sine squared phi, and of course this term here is 1, so this is f naught squared. Okay, so now I've got an expression for essentially a in terms of f naught without any phase terms in this thing. What we need to do here is solve it for a. And so what we can do out the front here is basically pull our a squared term out the front. So it's now going to be k minus m omega squared plus c squared omega squared, like so. Oops, let me just make sure I got my bracket right. Good. And we can now push that over to the other side. So our a squared is going to be f naught squared on this guy, k minus m omega squared squared plus c squared omega squared, like so. And of course we can take the square root of both sides in here, and rather than writing this all out again, I'm just going to get rid of these two squares here and put a factor of a half just here, okay? And of course, the amplitude here is also a function of our frequency, okay? And so you can see this in the terms. C is a constant, K is a constant, M is a constant. F naught is probably a constant. We might tune it, we might not. And if we did tune it, then what we might do is write that A is a function of omega comma F naught. And it's a function of our frequency, okay? All right, so we can call this thing equation 4 because it's actually now a really useful little result in here. Okay, so this is the form that you will sometimes see it in books, and you will sometimes see it in books in a slightly different form, and I'm not going to go through and do every step to transforming between the two because it's a neat little simple algebra exercise, but I'm going to point out quickly how to do it. So we know from the last couple of lectures that we've got two relations here. We've got omega naught squared is equal to k over m, which has the usual omega naught is equal to square root k over m that you've seen before. And we can define a gamma that we call C on 2m. And we defined this parameter yesterday when we were doing damped oscillators. So if you don't remember it, you might want to go back there and have a look. We can take those two things and we can write them instead as k equals m omega naught squared and c equals 2m gamma, like so, okay? And now if what you do is you take the k and you substitute it in here and here, and you then take the c that you've got and you substitute it into there and there in those two equations, you can rewrite those two equations a little bit like this. What you get is tan phi is equal to 2 gamma omega on omega naught squared minus omega squared. And your amplitude becomes f naught on m divided by omega naught squared minus omega squared squared plus 4 gamma squared omega squared to the power of a half. Okay, and this thing here is something that we often call the resonance denominator. It's often given the term d omega. And so we would write this thing rather simply as f naught on m divided by d omega. Okay. Okay, so an interesting question at this point, and we can call this thing 3a, and we can call this thing 4a if we want, right? Okay, so the interesting question at this point is, why did we even do that? The reason why we did that is that if you think about equation 3 and equation 4, we've got our phase and our amplitude tied now to quantities of the physical system. So a mass, which means we must have a body. We've got a spring constant, which means we must have a spring. We've got a C, which might be tied to, for example, a damping mechanism or air resistance or something like that. Sometimes what you want, particularly when you've got a physical behavior that's common amongst different systems, and resonance is a case here, like a forced harmonic oscillator, you can imagine a spring being driven by some mechanical thing. You can imagine the example we had in the video where you've got basically a mechanical object or just a physical object being driven by a sound wave. You can imagine the example that I'll show in the second half where you've got an electrical circuit, so there's no moving parts whatsoever. Well, electrons are moving, so maybe they're the moving part in response to some electromagnetic excitation. And so sometimes what you want to do is be able to pull out the things that are connected to a physical system and connect them to just a thing where you can plug this in. And if you think about these two new equations down here, 3a and 4a, now they're just connected to frequencies omega, omega naught, and a forcing term f naught and a damping term gamma. And what we can do is we can find that we can get other systems, you know, for example, a resonance circuit, and all we have to do to use the same equations is just work out what gamma and omega naught correspond to in the physical parameters of that system. Okay, so this is actually a fairly common thing in physics. When you get behaviors that are common between different physical systems, you try to detach the physics from the specific system so you can use it as more a universal effect. Okay, all right. So before we take a break, there's one last thing I want to do here, which is we're interested in amplitude, and often we're interested in maxima and minima. And we know in this system from the wine glass demonstration we saw at the start that basically we can drive oscillations in here. And so the interesting question is, when do we get to the point where we get the maximum amplitude of oscillation from our driving, okay? And so we're interested in amplitude, and if we're interested in a maximum, that means we need to take a derivative and make it equal to 0, okay? So what we're looking for is max amplitude, and so that's going to be dA on d omega is equal to 0, and of course this is going to be d on d omega of f naught on m d omega, like this, okay? Now, one thing we can do here is we know that f naught and m don't depend on omega, right? So what we're really looking to do here is make d on d omega of 1 on d omega equal to 0. And what this really means is that we want d on d omega of omega naught squared minus omega squared plus 4 gamma squared omega squared to the minus a half to be equal to 0. So we need to get the derivative of this thing in here, okay? All right. The way we can do this most easily is to use a thing called the power function rule. So what we can write this thing as is d on d omega. And I'm going to introduce a new function here just to make this workable that is basically g of omega to the minus a half equals 0, okay? And so this g of omega here is basically just this bit inside the square brackets, all right? And I'm going to do this because my power function rule, which you won't find in all the derivative tables. Some call it this, some don't. I like it. It's one of my favorite rules to keep. And again, it's one of those things I had in my book, and that's why I can always go look it up. D on d omega, g omega to the n is going to be n g of omega n minus 1 times g dash omega. Okay, so to solve this thing, all we need to do here is get dg on d omega, but to do that we need to clean our g of omega up just a tiny bit. Okay, so we've got our g of omega, and what we're going to do is take it from the version that we've got up here, and just expand that out so the terms are a bit clean and it's easier to get a derivative for. Okay, so this thing is omega naught squared minus omega squared, omega naught squared minus omega squared, plus 4 gamma squared omega squared. And then of course we can multiply out these brackets. So this is going to be omega naught to the power of 4 minus 2 omega squared omega naught squared, plus the last term here, omega to the power of 4, plus 4 gamma squared omega squared, okay? And then, of course, you'll notice that there's some terms in omega squared. There's some terms in omega to the power of 4, and there's some terms in omega to the power of 0, which is 1, right? So we can write this like this. It's going to be omega to the power of 4, so the omega terms, we know that omega naught is at the moment a constant, because it's k over m, or square root of k over m. Omega is a variable, so now we're writing essentially a quartic equation, right? So this is omega to the power of 4 plus 2 omega squared, 2 gamma squared minus omega naught squared, plus omega naught to the power of 4. Okay, so there's a omega to the 4, omega to the 2, and 1 on the end, and the cubic and linear terms don't exist in this particular equation. And now it's really easy to get a derivative for, right? So g dash omega is 4 omega cubed plus 4 omega 2 gamma squared minus omega naught squared, and of course this term on the end is a constant in omega, so it just vanishes, right? Really simple. And so then our power function rule tells us that the derivative that we were after is going to be, so we wanted d on d omega of g of omega to the minus a half, like so, okay? So this is going to give us a factor of minus a half out the front. Then we're going to get g of omega to n minus 1, so it's now going to be g of omega to the minus 3 half. And then we're going to have a term of g dash omega, on the end here. So, and this of course will be equal to 0. So this thing is equal to minus a half 4 omega cubed plus 4 omega 2 gamma squared minus omega naught squared divided by basically our big fat term here, omega naught squared minus omega squared squared plus 4 gamma squared omega squared to the square bracket 3 halves. Okay, and of course it looks more imposing than it really is. It's a big equation, but the way to make it 0 is that we make the numerator go to 0, right? And so that actually is not too scary. We can act the half through that whole thing at the top. The minus sign vanishes because you can use the 0 to clean this up. So what we're really looking at here is 2 omega cubed plus 2 omega 2 gamma squared minus omega naught squared is equal to 0. And then of course we can let's see here, what can we do? We can go 2 omega cubed is equal to minus 2 omega 2 gamma squared minus omega naught squared just here. We can cancel out the 2, we can cancel out one of the omegas, so this is now omega squared is equal to minus 2 gamma squared minus omega naught squared. And of course we no longer need to keep the term in the end in brackets, so this thing can basically become omega naught squared minus 2 gamma squared up here, okay? And then of course we have to take the square root of this thing, so omega is equal to square root omega naught squared minus 2 gamma squared. And this is a thing that we call the resonance frequency. It's basically where the amplitude is a maximum. So it's the point where you get the most response for the input force that you put in. And so we often call this omega R. It's our resonance frequency. Pops out quite nicely when you take that derivative, okay? And so you can see at this point, actually, just if we step back for 1 second, our omega naught squared is k over m, and our gamma in here is c over 2m. And so we still have this resonance frequency being tied to physical parameters, right? It's some balance between the spring constant, the damping constant, and the mass, okay? And so the driving force itself doesn't turn up in determining where that resonance frequency is. That resonance frequency is set by the system itself. And so this is why you have any oscillatory system and you have a natural frequency for it. It's because there's a frequency that's specified by the physical parameters of that system that you then take your excitation source and tune that to in order to get your resonant behavior out. Okay, so this is completely tied to terms that are in just the oscillatory system we're dealing with. Okay, so I'm going to take a quick break at this point, and then we'll come back and look at weak damping limit and strong damping limit a little bit, and some more details of what happens at this amplitude peak that we call the resonance.